In Lesson 2, we'll have some more concept review of basic algebraic concepts as well as some geometry review. And if you recall, the meshing of algebra and geometry is in a concept titled analytical geometry. Some people call it coordinate geometry as well, because we use the Cartesian coordinate system as our basis for meshing these two concepts together. There's lots of different topics they want you to review, so I think the best way to learn these, as I think learning any mathematical concept, is by doing problems and working them out. I'm not going to cover in a lot of detail what is in the lesson. If there's some certain definitions and rules that you think would be good to put in your formula notebook that you're making, then go ahead and write those in. But you'll need to review through the lesson some as well as do the problems that I'm going to cover. Look at this problem. It says find the distance from the midpoint of the segment joining -2, 3 and 4, 5 with -1, 4. Now just keep in mind all of this is review, so if you want to, pause the CD and see if you can find the answer to this problem on your own. Then fast forward to the answer on here. If you got it right, just go on to problem B. If you got it wrong, rewind and see what your mistake was. Anytime you have a problem dealing with points, you know that you can look at that problem in an analogous way by using the Cartesian coordinate system. And so that's what I'm going to do first, is just put these points on a Cartesian coordinate system to help me see what the problem is going to look like and kind of estimate what the answer is going to be. We can just put some tick marks on this Cartesian coordinate system, try to make them as evenly spaced as possible. And then we can go ahead and put some points on here. The distance from the midpoint of a segment joining -2, 3 and 4, 5. So we go to the left 2 and up 3. And then we'll have 4, 5. So that'll be to the right 4 and then up 5 would be about right there. This line segment would run about like that. And we want to find the distance from the midpoint of that segment. So just estimating here, the midpoint would probably be around there somewhere. And we want to find the distance from there to the point 1 or -1, 4. So that would be to the left 1 and up 4, which would be about right here. So really what we want is this blue line segment. We want to know how long that blue line segment is going to be. It looks like it'll probably be less than 2 units long or something close to that. What we need to remember to solve a problem like this is the Pythagorean Theorem. Think about that red line segment that we have drawn there. If we made a right triangle based on that, we could see that this height here would be 2, and then our horizontal distance, we started at -2, went over to +4, so this side would be 6. We could find that hypotenuse, or the line segment, basically by just using the Pythagorean theorem. We also rearrange that and have another form called the distance formula, which is just equal to the square root of the differences in our x values plus the differences in our y values squared. So if we know 2 points, we can figure out the distance between them using this formula. We want to find the distance from the midpoint of that red line segment. So remember how you do the midpoint, how you find the midpoint of a line segment like that? X, I'll just call it x subscript m for midpoint. That would be equal to the sum of your x values, -2 plus 4. You divide it by 2. It's basically kind of like an average. So that would be 2 over 2. That's 1. And then y subscript n, the midpoint for y, would be the 2 y values, 3 and 5, over 2. So that would be 8 over 2 is 4. So that's our midpoint, is 1, 4. That means we want to find the distance between -1, 4 and 1, 4. Now, all we have to do is substitute that into the distance formula. The square root of the difference in the x values, it doesn't matter which one we choose first because we're squaring it, so it'll end up being positive. We'll do minus 1, that would be a negative 2 squared, and then plus the difference in the two y values, it's just going to be 4 minus 4. So that'll be 0, and we'll end up with the square root of 4, which equals 2. And that's what we were estimating using our Cartesian coordinate system. We thought it might be about 2 units long, and indeed it was. If we had used graph paper to draw this problem, we could have seen probably that we didn't even need to use the distance formula since it was just a horizontal line. That blue line segment is just a horizontal line, and since both the y values were the same, we could have just looked at the difference in the x's and seen, oh, they're 2 apart, so its distance is 2. We applied 2 rules here to find a new truth. That's what deductive reasoning is. It's applying rules to learn new things. We used our midpoint formula, where it's just the sum of the x values over 2 to find the midpoint of the x coordinate, and then sum of the y's over 2 to find the y coordinate for the midpoint. We used our minus 1, 4 point with our midpoint of the red line segment. We substituted those into the distance formula to find the distance. Look at problem B. Find the equation of a line that is parallel to that general form for the equation of a line 3x plus 2y minus 4 equals 0 and passes through that point 3, 1. Now, remember parallel lines, those have the same slope. And something that if you've done any of my CDs before, you know that the first thing I want you to do when you want to find the equation of a line is write down the standard form of the equation of a line, and that you use that as a pattern to help you think about what you're doing. Okay, here's my formula. I need to find m, which is the slope of that line, and I need to find the y-intercept. I can find the slope if I set this equation that they gave me, set that into the y equals mx plus b form. That's called the slope-intercept form. If I change that general form to slope-intercept form, then I can figure out the slope of my line that I'm trying to find here, because parallel lines have the same slope. Then I can substitute the point 3, 1 in and solve for the y-intercept. So why don't we get this general form that they've given us in slope-intercept form, y equals mx plus b form. And so we'll say 2y is equal to minus 3x plus 4. Divide everything by 2, and we'd have y equals minus 3/2 x plus 2. So the slope is minus 3/2. Perpendicular lines, their slopes are negative reciprocals of each other. So if we were trying to find the equation of a line that's perpendicular to this one, its slope would be positive 2/3. But we're finding the line that's parallel to this one. Their slopes are the same. So in our standard form, we can just say y equals negative 3/2 times x plus b. We know our slope. We need to find our y-intercept, and we can figure that out by just substituting that point 3, 1 into this equation, and we can solve for the y-intercept. So y is 1 when x is 3, so we'll have minus 3/2 times 3 plus b. 1 is equal to minus 9/2 plus b. So b equals 9/2 plus 1, or 2/2, so that would be 11/2. Our equation, therefore, is y is equal to minus 3/2 x plus 11/2. Has the same slope as the other equation. Different y-intercepts, though. Parallel lines, their slopes are the same. Perpendicular lines, their slopes would be negative reciprocals of each other. Working with equations of a line is going to be a super important concept in the study of calculus, especially in differential calculus. We can break calculus up into two main groupings, differential and integral calculus, and in differential calculus, working with an equation of a line is really important. So it's very, very important to know what slope is, know what y-intercept is, know the different parts of the equation of a line, especially the slope-intercept form. Sometimes you might be asked to find the double-intercept form. Let's just look at our slope-intercept form that we have here and convert that to the double-intercept form. And let me just show you how you do that. First, you get the y and the x term on one side, and we'd have y plus 3/2 x is equal to 11/2. And what you do is divide everything by 11/2. So basically you set everything equal to 1. And divide everything by 11/2. Then what you want to do is just leave the y, leave it over 11/2. Just keep that in the denominator, because that's basically your y-intercept, right? That's what double intercept is about. Whatever the denominator of that y term is, that's your y-intercept. And then the denominator of the x term, we need to work on this one a little bit. Simplify that to 3/11 times x equals 1. And then we need to change that 3/11x. If we had that in the denominator, wouldn't that be the same thing as 11/3? We could just say x over 11/3, like that. So there's our double intercept form for that equation. Think about it. When x is 0, y would equal 11/2. When y is 0, x would equal 11/3. That's why it's called the double intercept form, because you can figure out the x-intercept and the y-intercept. And those are 2 points, aren't they? That's all you need to define a line, is 2 points. Let's look at practice problem C. I want you to solve this by completing the square. So remember what you do on these. You set it equal to 0. 2x squared minus x minus 4 equals 0. And when you're solving for an equation like this, you're solving for the roots. Sometimes we call them zeros as well. And if you remember the completing the square method, you can't have a coefficient other than 1 in front of the x squared term. So we have to factor a 2 out here. And that means basically divide everything by 2, including the 0 on the right side. If we're using just our typical algebraic rules, you have to divide everything by the same non-zero number, and we end up with x squared minus 1/2 x minus 2 is equal to 0. Now we can use completing the square, and what we'll do here is put a set of parentheses like that. We'll have our x squared minus 1/2 x in that, and then the minus 2 on the outside, and just move that minus 2 over. X squared minus 1/2 x, leave yourself some space, close the parentheses, equals 2. Put that 2 on the right hand side. Now to complete the square, what we're trying to do there is just get a squared binomial on the left, turn that trinomial that we're going to make into a squared binomial. We take half of the x coefficient, which would be a negative 1/4, and we square that. So that would be negative 1/4 times negative 1/4 would be a positive 1/16. Add that on the left. That means we have to add it on the right side as well of that equal sign, or we're going to change the formula. So we add it on both sides, and on the left we end up with x minus 1/4, half of that x coefficient squared. That's what the left side's trinomial would equal. We could factor it into that squared binomial. And then on the right, we have basically 33 over 16. Now we can take the square root of both sides. That's the whole purpose for completing the square on a quadratic equation like this. If we take the square root of both sides, we get rid of that squared term, and we're able to just solve for x. And so we'll have x minus 1/4 is equal to, anytime you take the square root, you have to do plus or minus. That'd be the square root of 33 over the square root of 16, which would simplify to a 4. Now we can move the 1/4 to the right side, and we get x is equal to 1/4 plus or minus the square root of 33 over 4. Now sometimes you'll have a negative number inside the radical sign on the right, and you just turn that into a complex number. Typically when you solve a quadratic equation, you get two answers. Here we have 1/4 plus the square root of 33 over 4, 1/4 minus the square root of 33 over 4. Now if you recall, there's another way to solve quadratic equations like this. That's called the quadratic formula. And if you have it in the form ax squared plus bx plus c equals 0, the quadratic formula is just x is equal to minus that coefficient of b plus negative b plus or minus the square root of b squared minus 4 times the a times that c coefficient, all over 2a. Let's apply that quadratic formula to solving this equation that we have. And what we need to do is look where we have it in standard form. That would be right here, what I'm circling in blue. 2x squared minus x minus 4 equals 0. There we can see that a is 2, b is negative 1, and c is a negative 4. So let's go ahead and substitute in. And now we should get the same answer that we did before, otherwise we did one of them wrong. Negative b, that would be a positive 1, right? Because we're doing negative times negative 1. Plus or minus the square root of b squared, which would just be a 1, minus 4 times a, which is 2, times c, which is negative 4. All of this over 2a, which would just be 2 times 2, or 4. So we have 1 plus or minus the square root of 1. We have two negatives there, so that'll be a positive 8 times 4. 1 plus 32 is 33 over 4. So that is the same answer that we had before. It's just broken up into that rational part, 1/4, plus or minus the irrational part. You know, that square root of 33 is an irrational number. So usually that's how we write the answers or the roots to these problems. Because a lot of times we end up with a negative number under the square root sign, and that means that's a complex number. And we always write complex numbers in the standard form a plus bi, where we have a real part and an imaginary part. So it's just good practice on these problems when they have an irrational part of it, just to write the real part separate and the irrational part separate. We could practice problem D. Let's review polynomial division. Divide that 3x cubed plus 2x plus 5 by x minus 2. So what we'll do here, if you remember, x minus 2 right here, and use your long division format, and you'll have 3x cubed. Then you don't have an x squared term, so you just say 0x squared plus 2x plus 5. And then you just start to try to eliminate each of those terms in your dividend, in your 3x cubed plus 0x squared plus 2x plus 5. So the first term is 3x cubed, and you think about your divisor, x minus 2. What could I multiply that by to get rid of the 3x cubed? It's just like if you had 18, or let's say 185 divided by 3. you divide that in long division format, you think about, well, what could I multiply the 3 by to get rid of 1? Well, nothing, but I could multiply the 3 by a 6 to get rid of that 18, because 3 times 6 is 18. And so subtract those, that would be 0. Bring down the 5. 3 goes into 5 one time, and so I'd have 3 times 1 is 3. I put that here. Subtract, get 2 as a remainder. 61 remainder 2. That's just like with numbers. Same idea with polynomials here. Think about that 3x cubed. If I multiplied by 3x squared, multiplied x minus 2 by 3x squared, I'd have 3x squared times x is 3x cubed, and then 3x squared times negative 2 is negative 6x squared. Subtract those, and you'd have 0x squared minus a negative, which is plus 6x squared. Bring down the 2x. And so now we want to get rid of that 6x squared. So we think, well, we could multiply x minus 2 by 6x, and we'd have 6x times x is 6x squared, and then a minus 12x here. And so we'd get the 6x squareds to cancel, and then 2x minus a negative or plus 12x would be 14x, and then bring down the 5. We want to get rid of that 14x now, so we could just multiply by 14, put that into our quotient. 14 times x is 14x. 14 times negative 2 would be a negative 28. 5 minus a negative or plus 28 would be 33. And so there's our remainder, and we write it 33 over x minus 2. So there's the quotient, or the answer to that division problem. 3x squared plus 6x plus 14 plus that remainder of 33 over x minus 2. Let's solve a system of equations now. You should know that anytime you have a system of equations and you're solving for unknown values in that system of equations, you have to have the same number of equations as you do unknowns. We have two unknowns here, x and y. So that means we need two equations. We've been given two equations, so we know that we can solve this system of equations. This is a non-linear system of equations. Maybe you recognize that bottom equation as the equation of a line. The top one may not be quite as familiar to you, but hopefully you remember that's the equation of a circle. So let's use our Cartesian coordinate system. That's where we mesh algebra and geometry together. And let's just kind of draw a picture of what we're doing here that will help us to determine what our answers might be. We have x squared plus y squared equals r squared. So the radius is the square root of 3, because square root of 3 squared would equal 3. And that means we have a circle that's about 1.7, because square root of 3 is about 1.7. It'd probably look something like that. And then we have that line, y equals x minus 1. What we can do there is just think about a y-intercept of negative 1. We'd start there, up 1 to the right 1. It's probably going to go somewhat like this. So we see 2 points here where the circle and the line intersect each other. And that's what we're looking for when we solve a system of equations like this, is where do those two functions intersect each other on a Cartesian coordinate system. And actually, a circle is not a function, it's a relation. So where these two equations intersect each other on a Cartesian coordinate system would be a better way to describe this. We should end up with 2 points, 2 xy points for answers here. So let's just use some of our common rules or applications when we're solving systems of equation. One of those is substitution. We can substitute one value into another to simplify it. Why don't we just substitute x minus 1 into the circle equation, and that would give us x squared plus x minus 1 squared equals 3. So see, now we have one equation with one unknown, and we'll need to expand x minus 1 squared out. We'll have x squared plus x squared minus 2x plus 1 equals 3. And we can see here that we have a quadratic equation. If we just move everything over to the left and set it equal to 0, we'll have 2x squared minus 2x minus 2 equals 0. Factor a 2 out and we'd have x squared minus x minus 1 equals 0. And we can use the quadratic formula now. Negative times negative 1, that'd just be a positive 1, plus or minus the square root of b squared, which would be minus 1 squared, be a positive 1, minus 4 times a is 1, times c is negative 1, all over 2 times a, which is 1, so that'd be equal to 2. And so then we'll end up with 1 plus or minus the square root of 1 plus 4, square root of 5, over 2, which is just 1/2, plus or minus the square root of 5 over 2. So that's what x is, right? Those are two values for x. So think about it. We're going to have 2 points we're solving for. Let's just go ahead and set up a couple of ordered pairs. One of them will be 1/2 plus the square root of 5 over 2, comma, we don't know what y is yet, and then the other one's going to be 1/2 minus the square root of 5 over 2, comma. Okay, look at our two original equations. Obviously the easiest one to solve for y would be the linear equation. Just substitute x in there. We'd have y equals, when x is 1/2 plus the square root of 5 over 2, then we'd have a minus 1. So really all we need to look at is the 1/2 and the minus 1. That would give us a negative 1/2 plus the square root of 5 over 2. So we'll put that right here. So when x is 1/2 plus the square root of 5 over 2, y is minus 1/2 plus the square root of 5 over 2. And then it's pretty easy to see the second point. This one would be minus 1/2 minus square root of 5 over 2. So here's our 2 points. We expected to get 2 points for answers, and we did. Using the Cartesian coordinate system to help us identify or estimate our answer, that was a good idea here because it helped us see what our answer might be. We saw we were probably going to have 2 points for answers, and we did get that, so that gives us confidence we did the problem correctly. Let's go ahead and do a few geometry problems. These problems involve application of some different geometry properties that if you know the property or the relationship, it makes the problem super easy. If you don't remember the relationship, it makes it really, really difficult, if not impossible, to solve. So you might want to review back through the lesson and write down some of those properties and relationships that they're having you review in addition to the ones that we're going to work on here. Put those into your formula notebook that you're making. In problem F, I want you to find x and y. Well, you should recognize there that you have a right triangle, so that means that side, or that, not that side, but that angle there is 90 degrees. And you also know that you have a 35-degree angle inside the triangle, so that means you could figure out x, because you should remember the sum of the triangles in a triangle equals 180 degrees. We just say 180 equals 35 plus 90 plus x, and so that would just be equal to 125 plus x. Subtract 125 from both sides, and x would equal 55 degrees. So y, that's a supplementary angle to x, So that would just be 125 degrees, because the sum of supplementary angles is 180. And the sum of those two would equal 180, wouldn't it? Now look at problem G. I want you to find x there. We have some segments inside a circle, and those are secants. Those lines that don't go through the center of the circle but touch it at 2 points, those are called secants. And the products of the segments that they're broken up into, those products are equal to each other. So in other words, x plus 3 times x plus 1 is equal to x times x plus 5. That's a property of intersecting secants inside of a circle, and that can be proven by looking at similar triangles. What we need to do here is just expand each of these relationships out. On the left, we have those two binomials to expand. X squared plus 3x plus an x would be 4x plus 3. And then on the right, we have x squared plus 5x. And we see there the x squareds cancel. We could move the 4x to the right side by adding a negative 4x to both sides, and we'd have 3 equals x, or x equals 3. So there's our answer. On that problem, we could substitute back into our original relationship and just see if that's right or not. 3 plus 3 times 3 plus 1, that would be a 6 times a 4. That's 24, equals, on the right side, 3 times 3 plus 5 is 8. 3 times 8 is 24. So we saw there both sides are equal to each other when x equals 3. That gives us confidence we did the problem correctly. Now in H, I want you to solve for x and for y. X is that angle, and look at what's happening here. We have one side basically intersects right here, so it's a tangent. That line segment on the outside of length y is tangent to the circle. And then the other one cuts through the circle and it forms a secant there. Now remember what happens on that? What you do is you multiply the outside length by the total length. See, this problem is similar to G, except in G the line segments intersected inside the circle. We could pretend like we continued these line segments off on practice problem H like that, and so we could say that angle's x as well because vertical angles are equal. Those line segments are intersecting outside the circle. On a problem like that, the way we find missing lengths of sides is to take the length on the outside by the total length of that segment. So on the bottom, we'd have 16 times 16 plus 9 is 25. That's going to be equal to the length of y. That's the outside length times the total length, which is still y because that's its total length, right? It doesn't intersect or pass through on the inside, so it's just y times y. 16 times 25 is 400. That equals y squared. Take the square root of both sides. Y would equal plus or minus 20. We just say 20 meters. Go ahead and write our units because we have like 9 meters, 16 meters. We know our lengths are in meters here. They don't always give you units on these problems, but on this one I put meters on there. We had a plus or minus 20 for an answer. Obviously you can't have a negative length, so you just put 20, positive 20 meters for the answer. Now the angle x, we need to find that. And remember, on a problem like this where you have line segments that intersect outside the circle, that vertical angle there is equal to the difference in the arcs, half the difference in the arcs that it intercepts. So look closely here now. This 89-degree angle, basically that's the arc from here to there. And then we have that 110-degree angle for the other part of the intercept, or 111-degree, actually, is what it is. So we say that x is equal to 111 minus 89 over 2. And so that's going to be equal to 22 over 2, which equals 11 degrees. That's what x is equal to, 11 degrees. Now remember what happens when they intersect inside the circle. When the segments intersect inside the circle, the vertical angles are equal to the sum of those intercepted arcs divided by 2. So there's some real basic geometry relationships there that are important to know with angles, with line segments intersecting inside and outside of circles. If you know the relationships that are involved there, then solving problems dealing with missing sides and missing angles is really easy. If you don't remember the relationships, they become really hard. That's why you should write them in your notebook, your formula notebook that you're making. Look back through the lesson, write down any of those formulas you think that would be helpful for you as you go about solving these problems. Part B of this lesson is on the graphing calculator, and throughout the Saxon calculus textbook they'll have different examples on how to do problems using a graphing calculator, and they use a TI-83 calculator. Now there's newer versions, there's like the TI-84, TI-84 Plus. These versions will work as well. They're very similar to the TI-83. In the examples that you'll see me using, I use a TI-83 Plus calculator. Calculators have their good and bad sides. They can be used to replace learning, but we don't want to do that. We want them to emphasize and to help us learn a concept better. Let's go ahead and do a practice problem, and let's learn how to graph y equals 2x squared minus x minus 4 in a graphing calculator, and then find the roots of this parabola. So look at the example I have on the screen here. Look at the top left. On the TI-83, there's a y equals button on the top left side, and you press that, and you get a screen that says y1, y2, y3, y4. Next to y1, you can hit equals, and then type in 2x squared minus 4. Now, if you're not sure how to type the x in, there's a button that says x, t, theta, n, and you just press that, and you should come up with an x. And then you just hit your squared button, minus, hit the x, t, theta, n button again, and then minus 4. Next, you want to hit the window button. And when that comes up, you want to type in your values like I show on the screen here. X min of -5, X max of 5. And when you do -5, don't hit the minus like the subtraction 5. Hit the little negative sign at the bottom of your TI-83 calculator. And then the X scale is 1, Y minimum -5, Y max 5, X scale 1, X resolution 1. Then you don't have to clear out of that screen. You can just go ahead and hit the graph button at the top right of your keypad. And a parabola should come up like the one shown here. If it doesn't, then go back and check your work, see what your mistake is. So now you have a nice graph of that quadratic function 2x squared minus x minus 4. Now let's learn how to find the zeros of that function, and if you remember, that means where it crosses the x-axis when y equals 0, in other words. So that would be here and here. And so there are two zeros we can tell here. One of them is a little to the left of -1, so that should help us think about what the answer should be, and then the other one is just to the left of +2. Let's use the graphing calculator to find the 0 on the left, and what we need to do is hit the second button at the top left of the calculator, then the trace button, and then the number 2. If you see the words above the trace button, it says calc, and so we're going to the calculate menu, and we hit second. It's like the second set of commands that that button has. And so second trace gets you to the calc. Number 2 on the calc menu is 0. So you hit that and it comes up and it asks you for a left bound. And so what you do is you use your arrow keys on your keypad the left and right arrow keys, and you move your little marker here until you are just to the left of that 0 on the function, and you hit enter, and you can see the numbers down here that come up for the location that we had when we made this screen. The left boundary is minus 1.382979, and then it will ask you for a right bound, and then you hit enter, and you can see our right bound is x equals minus 0.9574468, and see that's to the right of where that graph crosses the x-axis. And then you put a guess in, and so you move the cursor again as close as you can to the 0, and we had x equals minus 1.170213, and you hit enter again, and it approximates the 0 for that function, minus 1.186141. To find the right-hand 0, just go to second trace 2 again, or calc 0 in other words, and you should come up with a 1.686147. And remember that the arrow keys, the left arrow key and the right arrow key, those are the keys that you use to move around on your graph of your function. The up and down keys, those don't work, so don't try to use those. Now, that was pretty easy to find the zeros. It's a lot easier than using the quadratic formula, and that's not the point of a graphing calculator, though, is just to make things easier. You still need to know how the process works, how the quadratic formula works, how to solve using the quadratic formula, because you may not always have a graphing calculator around. The best thing for you to use a graphing calculator for in a problem like this is to check your work. Another good use is in science, like in your science classes, when the goal of the class is not to see if you understand your mathematics formulas. The goal is to apply that mathematics to solve some type of scientific problem. In math, though, the best use of it usually is a way to check your work. So get familiar with your graphing calculator, make the most of this tool that you've been given. Okay, well, that's all for lesson 2.